Now we can talk about the very important topic of rationalizing. So throughout this module, we have seen a few fractions involving radicals. Notice that so far, no final answer has involved a radical in the denominator. And in fact, I have crafted every fraction to make sure that this never happened, that it never was a result, that a radical was left over in a denominator. Now, why would I do that? This is a tricky issue. Having a radical in the denominator is considered, quote, in poor taste in mathematics. Now, why would mathematicians think this? One way to think about it is, if there are multiple fractions that need to be added or subtracted, it's helpful if all the denominators are integers so that we can find a common denominator. A more general way to say it is, if there are multiple ways to write an answer, it's helpful if there's an established convention so that everyone writes the answer the same way. And that makes it much easier to compare whether two different people have found the same answer. So for whatever reason, the mathematical convention is to avoid radicals in the denominator. Now, if a radical appears in the denominator as part of the problem, and of course it sometimes happens, we need to change the fraction to an equivalent form so that no radical appears in the denominator. This process of change is called rationalizing the denominator. That is to say, making the denominator a rational number, an integer, rather than an irrational square root. So, suppose in the course of solving a problem we found x equals 12 divided by root 3. Let's pretend that we did all the math correctly. We got this as our correct answer. This is our solution to the problem. That might be mathematically correct, but because it's not rationalized, we won't find it among the answers listed in this. We won't find the answer listed in that particular form. You see, all the answers on the test are rationalized. So we need to rationalize anything that we find to match it to the answer choice. If there's a single radical in the denominator, we rationalize simply by multiplying by that radical over itself. So we're just going to multiply by the square root of 3 over the square root of 3. And of course, in the denominator, we get root 3 times root 3. Well, think about this. Root 3 is the number which, when we square it, we get 3. So here we're multiplying it by itself, so it becomes 3. Then we can cancel the 12 divided by 3. That becomes 4. We get 4 root 3. That is the rationalized form. So the answer would never be written in the form 12 divided by root 3. It would be written in the form 4 times root 3. Practice rationalizing the following. In each case, you're just going to multiply by the radical over itself and then simplify. Pause the video and then we'll talk about this. Okay, in that first one, obviously we will multiply by root 5 over root 5, and we get root 5 over 5. In the second one, we'll multiply by root 3 over root 3. We'll wind up with 2 root 3 over 3. In the third one, we'll multiply by root 21 over root 21. We get a 21 in the denominator. That allows us to cancel a factor of 7 and wind up with 2 root 21 over 3. Those are the rationalized forms. Even if there's addition or subtraction in the numerator, divided by a single root, all we have to do is multiply by the root over itself. So for example, if we had something like 4 minus root 6 over 2 root 3, really the only thing that concerns us is that root 3 in the denominator. So I'm going to multiply by root 3 over root 3. In the denominator, I get a root 3 times a root 3, which is 3. In the numerator, I distribute. That root 6 times root 3, remember that root 6 is root 2 times root 3, so we can multiply the two factors of root 3 together to get 3, and then we're just left with a root 2 left over. So what we wind up with is 4 root 3 minus 3 root 2 over 6, and that is the fully rationalized form. Things get trickier when we have addition or subtraction in the denominator. So suppose we had to simplify something like 2 divided by the quantity root 5 minus 1. Well, what we have been doing is not going to work here. You see, if we multiply this denominator by root 5 over root 5, we would have to distribute across the subtraction in the denominator. The root 5 times the root 5, that would equal 5. That would be fine. But of course, there'd also be a 1 times root 5, and that would be root 5, and our attempt to rid the denominator of radicals would not be successful. We have to make use of a different trick. So I'll say, remember the difference of two squares formula from the algebra module. P minus Q times P plus Q equals P squared minus Q squared. If this is an unfamiliar formula, I highly suggest go back to the algebra modules and watch the videos concerning this particular formula. It's one of the most widely applicable formulas in all of mathematics. So in other words, what we have here is the product of a sum and a difference has the result of squaring both terms. If P or Q, or even both of them, were radical expressions, then on the right side of the equation above, every radical expression would be squared, and there would be no radicals in the result. Very interesting. Consider any two-term expression, either addition or subtraction, in which one or more of the terms is a radical. So we might have things like this, for example. Two terms, and we're either adding or subtracting, and one or both of the terms is a radical. If we change the addition or subtraction to its opposite, we construct what is called the conjugate expression. So that first one, we have 3 minus root 7. The conjugate would be 3 plus root 7. In the second one, we have root 13 plus 2 root 11. The conjugate will be root 13 minus 2 root 11. So how is this helpful? Well, if we multiply any expression with radicals by its conjugate, one conjugate plays the role of a plus b, the other plays the role of a minus b, so that their product is the difference of the squares of the two terms, a squared minus b squared. So for example, if we had 3 minus root 7 times 3 plus root 7, well, essentially what we have here is an a minus b times an a plus b. And of course, this is going to equal a squared minus b squared. Or in other words, 3 squared minus root 7 squared. Square each one of them, we get 9 minus 7, which is 2. So in other words, we multiplied two expressions with radicals, and we get a product without radicals. That's a really big idea. This provides a clue we need for how to rationalize a fraction with a radical expression involving addition or subtraction in the denominator. So let's go back to that one that we couldn't solve a moment ago. We had something like 2 divided by the quantity root 5 minus 1. Well, what I'm going to do is multiply the numerator and denominator by the conjugate of the denominator. To rationalize, we're going to multiply the numerator and the denominator by the conjugate of the denominator. So what we have in that denominator is root 5 minus 1. The conjugate would be root 5 plus 1. So we're going to multiply by that conjugate. Root 5 plus 1 over root 5 plus 1. Then in that denominator, we have an a minus b and an a plus b, so we'll get an a squared minus b squared in that denominator. The numerator I'm just going to leave undistributed for a moment. And so we get a root 5 squared minus 1 squared. That will be 5 minus 1, which is 4. Then I can cancel a factor of 2 in the numerator and denominator, and I get root 5 plus 1 over 2. And that is the rationalized form. Incidentally, you don't have to know this for the test, but that happens to be the golden ratio. So rationalize the following. You will need to multiply the denominator by its conjugate. So I'm going to say pause the video and try this on your own. Okay, so we have a root 7 minus root 3. And so what we're going to need to do is multiply that denominator by a root 7 plus root 3. So we have to multiply root 7 plus root 3 over root 7 plus root 3, multiplied by the same thing over itself. In the numerator, I'm not going to distribute just yet. In the denominator, I get the square of those terms, the difference of the squares, which is just 7 minus 3. 7 minus 3 is 4. And then cancel 8 divided by 4. And we get 2 times root 7 plus root 3. And that is the fully rationalized form. Now we can distribute if we want to, depending, doesn't matter. The answer could be written in either of those last two forms. Rationalize the following. You will need to multiply the denominator by its conjugate. Pause the video, work on this, and then we'll talk about it. Okay, so we have a 3 plus root 5 in the denominator, so we need to multiply that by a 3 minus root 5. So we need to multiply both the numerator and the denominator by 3 minus root 5. In the denominator, we're just going to get the difference of two squares, 3 squared minus root 5 squared. In the numerator, I'm going to have to FOIL, and so what I get is the product of the first. 4 times 3 is 12. The product of the outer, 4, so that's minus 4 root 5. The product of the inner, that's plus 6 root 5. And then the product of the last, which is 2 root 5 minus negative root 5. Well, the root 5 times the root 5 is 5. 2 times 5 is 10. So that's just minus 10. Now we'll simplify everything in the numerator and the denominator. We wind up with 2 plus 2 root 5 over 4. Everything is divisible by 2, so we can divide by a factor of 2, and we are left with 1 plus root 5 divided by 2. Here's a practice problem. Pause the video, and then we'll talk about this. Okay, so we need to get x by itself, so of course we're going to divide by everything in the parentheses. We have an expression in the denominator involving addition or subtraction with a radical. So we're going to multiply by the conjugate. We have a 2 root 5 minus 3. We need to multiply that by a 2 root 5 plus 3. And so I'll multiply by that. In the numerator, I'll just leave it undistributed. In the denominator, I'm going to get 2 root 5, that thing squared, minus 3 root squared. And of course, 2 root 5 squared, as we learned from our operations with radicals a few videos ago, that's 2 squared times root 5 squared, 4 times 5, which is 20. And of course, 3 squared is 9. 20 minus 9, we get 11. We can cancel a factor of 11 in the numerator and denominator, and we're left with 5 times the quantity 2 root 5 plus 3. And that is the fully rationalized form of the answer. In summary, to eliminate roots from the denominator of a fraction, this is called rationalizing. And it's something you always have to do. The test answers, the answers that appear on multiple choice, will always be rationalized. And so we will have to rationalize to match our answers to this. If the fraction has a single root in the denominator, we rationalize simply by multiplying by that root over itself. If the denominator of the fraction contains addition or subtraction involving radical expressions, to rationalize we need to multiply by the conjugate of the denominator over itself.